You've probably heard of the concept of number systems, but never really gave it much thought. Or you've probably performed actions or operations based on the principle of number systems, but you never really thought you were working with number systems per se. There are several number systems currently in use. In theory, a number system can be based on any number greater than 1. The base 2 number system, known as the binary number system, is the foundation for digital electronics. Other number systems in use are the base 8 number system, the base 16 or hexadecimal number system, and of course, the one we are most familiar with, the decimal number system. I will explain how number systems work and how they are created, and after that, I will show you how you can create a number system based on any number. Although the base 8 and base 16 number systems are not as popular as the decimal or binary number systems, I like to think of them as behind-the-scenes number systems. The base 2 or binary number system is also a behind-the-scenes number system to most people, but it has nonetheless assumed a prominent place in our imaginations because of its importance in digital electronics. Now let me discuss the number system we are most familiar with, and which is more relevant to our study of math. Even though we are familiar with it, we generally don't think of the decimal number system as a number system. Even when we were in school, we never realized its significance. As long as the teacher marked the answer as correct, we never stopped to ponder what it actually meant to carry 1 and call it 10. Addition, subtraction, multiplication, and division all rely on number systems. When we carry or borrow, or when we divide, multiply, subtract, and bring down, that is when we perform long division, we are affirming the principles behind the decimal number system. But why are number systems necessary in the first place? Why even bother developing them? Well, if the decimal number system did not exist, we would have to represent all numbers, regardless of their magnitude, with a single unvarying symbol. The symbol could be as simple as strokes, squares, triangles, or circles, or it could be more complicated. Whatever was chosen, that symbol alone would be used to represent all numbers. The number of units of the symbol representing a particular number will be equal to the magnitude of the number itself. For example, if the stroke was the symbol chosen for representing numbers, the number 2 would be indicated by 2 strokes, like so. While the number 15 would be written with 15 strokes, like so. You can see how impractical it would be if we had to write down the number 1000. Imagine drawing 1000 strokes, circles or squares. But so much for theory. Let me explain the principle behind number systems. And once you understand this principle, you'll be able to devise a number system based on any number, because they all conform to the same principle. As I said in the introduction, one of the advantages of number systems is that they make it possible to represent large numbers conveniently. Imagine if we had to write down the number 30 using strokes. We would make 30 strokes. Now this is not the most tedious thing you could do by any means, but it is certainly inconvenient. To determine the values of numbers in this system, we would have to count the number of strokes for every number we wrote. Now this method of representing numbers might have been adequate in the beginning of humanity, when things would have been much simpler. If you sold 30 animal skins to your neighbor, you would make 30 marks on a tree bark or a piece of rock, and so on. But as economic transactions became more complex, a need for a more convenient and reliable way of representing numbers likely arose. When you compare it to the familiar way of representing the number 30, the advantages of the decimal number system are immediately obvious. Writing the 2 symbols that make up the number 30 is much more convenient than drawing 30 strokes or making 30 marks on a piece of durable material. It also leaves less room for error. It would be easy to write 1 more stroke or 1 less stroke than we intended to write if we were using strokes as a means of representing numbers. However, using the symbols of the decimal number system, we will be unlikely to make an error when writing the 2 symbols that make up the number 30. They are distinct and clear enough. So how does the decimal number system make it possible to represent numbers in a way that is scientific and functional? Well, the inventor or inventors decided to create a number system based on the number 10. To do this, they created a place value system wherein the place values increased from right to left by a power of 10. That is, each place value was 10 times the place value to the right of it. The first 6 of these place values are as follows. Every column or place value represents a power of 10. As we move from right to left, each place value is 10 times the value of the place value to the right of it. So for example, the number above, which we would read as 7,732, could also be read as 7 thousands, 7 hundreds, 3 tenths, and 2 units. To make it easier to understand, it might be helpful to think of the values in the plural sense. That is 7 thousands, 7 hundreds, 3 tenths, and 2 units. Saying it this way gives a better idea of the different powers of 10 and the place values involved. It will also be very helpful to compare the place values to denominations of a currency, like the American currency for instance. And when we tackle long division, multiplication, addition, and subtraction, you will discover the parallels between the steps used in these mathematical operations and day-to-day currency transactions, such as changing larger bills into smaller denominations and exchanging bills of a smaller denomination for a larger denomination of equivalent value. Some believe the decision to use the number 10 was inspired by the fact that we have 10 fingers. I don't know for certain. Whatever the reason, a number of digits equal to the number chosen for the base was developed. In the decimal number system, these units are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 digits in total. Same number of digits as the number the system is based on, which is 10. And by using just these digits, we can represent any number. And the value of the number will depend on where these digits are positioned within the number. The positions they occupy relative to one another, that is. For any number system, the digits are always numbered from 0 up to 1 less than the number base itself. Thus, the digits of the decimal number system are numbered from 0 to 9, and 9 is 1 less than the number base, which is 10. These 10 units, 0 to 9, are the workhorse of the decimal number system. For example, a number as large as 1999 can be represented with only 2 different symbols, because the position of each digit determines its value. The digit 9 is 9 if it is in the ones place, or if it is in the units place. It is 90 if it is in the tens place, and 900 if it is in the hundreds place. The value of 9 depends on the place value the digit 9 occupies. The digit 1 is 1000, of course, because it is in the thousands place. And going from left to right, each place value is 10 times the value of the next place value. And going from right to left, each place value is 1/10 the value of the next. Thus, the number above is 1000 because it has 1 in the thousands place, 9 hundreds, 9 tenths, and 9 units, which we conventionally describe as 1999. A number system is important for another reason. Rather than inventing an original name for every number imaginable, we can name larger numbers using the names of numbers which make up smaller subunits of the larger number. For example, the number 3426, which we read as 3426, is made up of 3 thousands, 4 hundreds, 2 tenths, and 6 units. These names, 1000, 100, 20, and 6, are names of the smaller subunits which make up the number. We can derive the name of any number using the names of the digits and or subunits of the decimal number system and the place values these digits and or subunits occupy in the number as a whole. Thus, we can easily name large numbers rather than developing a distinct name for every individual number. For example, the number 124 is made up of the digits 1, 2, and 4. Looking at the name of the number itself, the word 1 is the name of the second digit in the decimal number system. The word 100 is the special name given to 10 tenths or 10 sets of 10. And the word 20 is also a special name given to 2 tenths. or 2 sets of 10. Finally, the word 4 is the name of the 5th digit of the decimal number system. By using the same 10 digits and by using the names given to powers and multiples of 10, we can name any number without having to create a name for it that would probably not be intuitive. Imagine if we had to count from 1 to 1 million. We would have to come up with a unique identifier for every one of those numbers, if not for the decimal number system. A number system spares us the trouble of having to do this. We can simply name numbers by looking at the magnitude of each digit in each place value. I will now perform an exercise that will demonstrate how useful and convenient the decimal number system is, as well as introduce us to some of the elements that form its foundation and make it possible for us to name large numbers with ease. I will count from 1 to 20 in the decimal number system, and in the process will introduce you to features about the number system that will recur as we progress to larger numbers. So to count to 30, we would go 1, 2, 3, 4, 5, 6, 7, 8, and 9. The next number should be 10, but 10 is what the number system itself is based on. That is, we are organizing our numbers in sets of 10. So instead of placing 10 in the units column, when we count up to 10, we zero everything in the units column, write 1 in the tens column to indicate we have a 10, and place 0 in the units column. This means we've counted up to 10 once, as indicated by the 1 in the tens column, and we are ready to continue counting to 10 again, as indicated by the 0 in the units column. So right now we have 110 and no units. The place positions give the digits their value. The 1 is in the tens place, so its value is 10 times what it would be in the units place. If there was no 0 to the right of the 1, it would just be the number 1. So we must leave the 0 in the units place. This spares us the trouble of having to come up with a symbol for the number 10. We simply use the same digits used to represent units, but write them differently to denote the value 10. Using a place value system like the decimal number system, the only symbols we will ever need to represent any value are the same symbols used to represent the digits 0 to 9. So we've counted up to 10, but we have 30 strokes to record, so we continue counting. From 10, which we can read as 110 and 0 units, we go on to 11, or 110 and 1 unit, then 12, or 110 and 2 units, 13, or 110 and 3 units, 110 and 4 units, or 14, 110 and 5 units, or 15, 110 and 6 units, 16, 110 and 7 units, 17, 110 and 8 units, 18, 110 and 9 units would be 19. The names of the numbers from 11 to 19 are not necessarily intuitive and can be considered special names. These names 11, 12, 13, 14, 15, 16, 17, 18, and 19 make it possible to name larger numbers in a way that is systematic and easily understandable. For example, just from the name 217, one can tell that the number is made up of 2 hundreds and 117. But let us continue. After the number 19, counting up one more unit would mean we have counted up to 10 for a second time. So we increment the value in the tens place to indicate this, that we have counted up to a second time. Then we zero out the units column so that we can start using it to count up to 10 yet again. We now have 2 tens and 0 units, which is written like this. If we had merely incremented the value in the tens place to 2, for example, without zeroing out the units column, our count would have gone from 19 to 29. It would have increased by 10 instead of 1. So we must always ensure we zero out one place value before incrementing the place value to the left of it. As I stated before, certain quantities in the decimal number system have special names. 2 tens are known as 20, 3 tens are known as 30, 4 tens as 40, 5 tens 50, 6 tens 60, 7 tens 70, 8 tens 80, and 9 tens are known as 90. Out of the 30 strokes, we have now accounted for 20 strokes. So let us keep going until we get to 30. Next after 20 is 2 tens and 1 unit, or 20 and 1, or more conventionally 21. To aid in understanding the decimal number system, it will probably be more helpful to think of 21 as 20 and 1. Today we say 21, but in the past, about a century and a half or so ago, the number 21 would have been called 1 and 20. In fact, if you read some old novels or other historical books, a character might be described this way. He was a young man of 1 and 20, which is the same as saying he was 21 years old. So 1 and 20, 20 and 1, or 21 all mean the same thing. But of course, you should stick to modern naming practices and say 21 instead of 1 and 20 or 20 and 1. But the reason it will help to think of 21 as 20 and 1 is because saying 20 and 1 intuitively tells you that you have two tens, which is 20 and 1 unit. Calling it 21 doesn't really give you as clear an understanding of its value as calling it 20 and 1 does. But let us continue on our mission to represent 30 strokes as decimal numbers. From 21 we go on to 20 and 2 or 22, 20 and 3 or 23, 20 and 4 or 24, and so on until we get to 20 and 9 or 29. At this point we've counted up to 9 yet again. We can't go higher in the units column since we've reached 9 and our number system is based on the number 10. No number in the units column can be the same or higher than the number base that we are working with. So since we've counted up to 9, we will increase the digit in the tens place to 3 to show that we have counted up to 10 3 times. We have 3 tens. This is our third 10 since we started counting. So we put 3 in the tens place and change the value in the units column to 0 so as not to confuse things. If we don't change the value in the units column to 0, it will mean that we went from 29 to 39, that our count increased by 10 instead of 1, which of course would be wrong. So we increment the value in the tens column by 1 to indicate that we have counted up to 10 a third time. We now have 3 tens and 0 units, which is written like this. And 3 tens, as I have already mentioned, has the special name 30. We have now counted up to 30.
That will conclude this introduction to the decimal number system and to number systems as a whole. Thank you for indulging me. Please like, comment, and subscribe. And until we meet again, stay well. Goodbye.